Hey everybody, we're just finishing up our section on equilibrium basics, and as we get close to the end of this part, I wanted to spend a little bit of time talking about the reaction quotient. Now, the reaction quotient, and you can read all about it right here, okay, these two things, is very similar to the equilibrium constant. Mathematically, it's actually exactly the same. So Q, the reaction quotient, equals the products, the ratio of the products over reactants. And of course this is, products raised to the power times products, however many products you have, over the reactants raised to the power times reactants raised to the power, on down the line. But products over reactants. Okay. K is a very specific reaction quotient when the reaction is at equilibrium. Q can be measured or calculated at any time, and that's what makes Q different than K. That Q encompasses that law of mass action, or that ratio, at any time in the reaction. K is one specific time, albeit K is probably the most important time, or when it's at equilibrium is probably the most important time. And so typically, when we do chemistry, it's very easy for us to calculate the initial concentrations or pressures of whatever we have in the reaction mixture, whether it's reactants or reactants in some products or reactants in all the products. We can calculate that, and then we can figure out what Q is. If Q equals K, we just happen to have a reaction that is at equilibrium. If Q is different than K, then that means the reaction has to move to get to equilibrium, that dynamic process. So there's two scenarios other than when Q equals K. Okay. What if Q is bigger than K? Well, if Q is bigger than K, and this graphic is very good at summarizing it, that means that Q needs to decrease, mathematically speaking, needs to decrease in order for this to be the same as K. So if I write this mathematically as products over reactants, the only way that I can get Q to get smaller is if I decrease, let's cancel that. Sorry. Okay. The only way I can get Q to decrease is if I decrease the numerator and increase the denominator. Chemically speaking, if I have reactants that are in equilibrium with products, the only way that I can get that to happen is if the reaction moves towards the left or shifts left. Okay? That way we're decreasing the amount of products, and because we're decreasing the amount of products, the amount of reactants will increase. Okay, now let me switch colors. Now what if Q is less than K? Well, I'm not trying to insult your intelligence, but, okay, I just want to step through it. Q needs to increase. Okay, well, if Q needs to increase, the only way to do that is by increasing the numerator and decreasing the denominator. And the numerator in this case is products. And so that means the reaction is going to shift to the right. And that's what this graphic shows. See, it shows the little shift to the right. Okay. Now, you can go ahead and memorize that if Q is greater than K, the reaction shifts left, and if Q is less than K, it shifts to the right. I prefer not to. I prefer to go through this this little mathematical logic puzzle to get me to the chemistry. That way I'm sure I'm going to get it right. Okay? Yeah, it's a shortcut to memorize which one is which, but I think it's better to know the chemistry and the math behind it. And so what we can do from here is, if we're given the initial conditions of a reaction, we're given an amount of reactants and products, we can tell which way the reaction is going to shift, whether it's to the right or to the left. And so, so reaction quotient is used a lot of times at the beginning of a reaction or the beginning of a problem to determine which way the reaction is going to shift to tell us where we're going to add x and where we're going to subtract x. Okay, so that's the information about reaction quotient.